Use the rational zeros theorem to list all the possible rational zeros of the following. This is a polynomial named g of x. It actually has degree 4, but it's actually not in descending order yet. What is the rational zeros theorem? The rational zeros theorem can be stated as follows. Let g of x equals this degree n polynomial in descending order with integer coefficients and a sub n not equal to 0. If g of x has a rational zero, then the zero can be written as p over q, where p is a factor of a sub 0 and q is a factor of a sub n. In other words, the only possibilities for rational zeros of g of x are the numbers of the form p over q, where p is a factor of a sub 0 and q is a factor of a sub n. The first thing we want to do for our example is write g of x in descending order. So notice we have a 3, x to the 4th is the highest power, and we're going to write that first. Plus 2x to the 3rd minus 9x squared minus a 5x and then minus a 2. And you can see that a sub n is 3. A sub 0 is actually equal to negative 2, and then a sub n is 3. In our case, it's actually a sub n is actually for n equals 4, if you're interested. So why do we write a sub 4? Now, the rational roots theorem says, or the rational zeros theorem says, if there's any possible rational zeros, they have to have the form where they are factors of negative 2 over the factors of positive 3. Why don't we list all such possibility? Rational zeros. Possible. The key word is possible. Possible rational zeros are, well, we need plus or minus 2 over, not plus or minus 2. We need plus or minus 1 first. Plus or minus 2 over plus or minus 1 and plus or minus 3. Why don't we list all such possible zeros in order? So what is the lowest possible zero here? That would be negative 2. Negative 2. What else do we have? We have negative 1, negative 1/3. I'm sorry. Why don't we go back a step here? We have negative 2/3, negative 1/3. What else do we have? We have a 1/3, 2/3. We also have 2. I believe that's it. we have all our rational zeros. Oh, I take that back. I forgot the number 1. So don't forget the 1, and then 2. Yes, those are all the possible rational zeros. I'm going to circle the final answer. By the way, this right here is not a circle. That's my version of a cloud, and a cloud means symbolic math. This is sort of cloudy math. It's really not the correct mathematical grammar. So I put that in a cloud because it's really more of a symbol, and it's not written in any text. The thing you do want to write is the final answer, and the final answer is definitely right here. Use the rational zeros theorem to list all the possible rational zeros of the following. Here's the rational zeros theorem again, in case you haven't written it down already. We already know that g of x is already in descending order. The highest power is first, and then there's the coefficient 9. So in our example, we have a sub 3 is 9, and we have a sub 0 is 4. The possible rational zeros for this polynomial is all the factors of 4 with the positive and negative symbols in front of it, over all the factors of 9 with all the positive and negative symbols in front of them. So plus or minus 1, plus or minus 2, and then plus or minus 4 could be the numerator. And in the denominator, they could be plus or minus 1, plus or minus 3, and then plus or minus 9. Let's see what our possible rational zeros are. Our possible, well, by the way, this is going to be in a bubble because this isn't correctly written. The possible rational zeros from our bubble are what is our lowest rational zero? It looks like negative 4. So we have negative 4. Is there anything between negative 4 and negative 2? And then, of course, negative 1, right? Well, we have a lot of possibilities here. We have negative 2/3, negative 1/3, well, let's list them in a different way. Why don't we do this quickly? So why don't we write this in a systematic way? Plus or minus 1, plus or minus 1/3, plus or minus 1/9. So there's 6 possible rational zeros. We also have what? Plus or minus 2, plus or minus 2/3, plus or minus 2/9. We also have plus or minus 4, plus or minus 4/3, and plus or minus 4/9. And that should cover all your possible rational zeros. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2, 18 possible rational zeros. Now that doesn't mean all of them are going to be a 0. There's no way, right? This is actually a degree 3 polynomial. However, if g of x has any rational zero, it will be of one of these forms right here. Notice g of x would have at most 3 real zeros. Here are the possible rational zeros. Circle our final answer. For the polynomial below, -3 is a zero. Express g of x as a product of linear factors. Well, we could use the factor theorem then. The factor theorem says if g of c for a polynomial evaluated at c equals 0, then x minus c is a linear factor. Knowing that, we actually have the remainder to be 0. So we are going to divide by the factor x plus 3. Notice our c here is actually equal to -3. So the shortcut for dividing x plus 3 into this polynomial is actually synthetic division. So even though I'm writing a division problem, I'm going to use the shortcut called synthetic division. Remember, synthetic division always works for a monic binomial, and monic means the 1 has to be a coefficient of the x here. A binomial means it has 2 terms. All right, how do we do synthetic division? Well, our c is -3, so I'm going to put -3 here. Now we're going to write the coefficients in descending order: 1, 7, 9, -9. And the first thing you want to do is perhaps draw a line here, bring down the 1, and we're going to multiply and add. Remember, all you have to do is 1 times -3, and then add it over here. So put a -3 here and add vertically. Notice you get a 4. And then you repeat this process. 4 times -3 is -12. Put it right there. And then we add. What do we got here? We got -3, and then -3 times -3 is +9. Put it there, and we add. And as expected, we were supposed to have a 0 remainder, and that 0 here is in fact this 0 there. What does this mean? What this means is that now we have actually rewritten g of x as this. G of x is one linear factor, x plus 3, multiplied to a polynomial that's 1 degree less. So that would be x squared plus 4x minus 3. And we want this in terms of linear factors. We now need to break this quadratic expression into 2 linear factors. Remember that -3 is a 0, so we're going to take advantage of that. I'm actually going to put a 0 here, and we're going to solve this equation. So if we solve this equation, we already know x equals -3. That's nothing new. But we want to do now is take x squared plus 4x minus 3 and set this equal to 0. I am actually going to complete the square here. So x squared plus 4x is now equal to this 3 over here. I need to add something to both sides and complete the square as well. So take this 4, divide by 2, we get 2, square it, we get plus 4, because 2 squared is 4. So I'm going to add 4 to both sides. And now what do we have? We have the quantity x plus 2 squared is now equal to 7. Take the square root of both sides. And now we have the absolute value of x plus 2 is equal to the square root of 7. X plus 2 is equal to plus or minus square root of 7. And we have x is finally equal to negative 2 plus or minus the square root of 7. We're not done yet. We need to write g of x as a product of linear factors. So g of x is equal to x plus 3. And in order to get linear factors here, we work backwards from here. We know that these are the zeros of the polynomial. So we are actually going to take a bracket here, x, subtract, let's say, negative 2 plus root 7. And then we'll also take an x and subtract negative 2 minus root 7. And that certainly will do it. To simplify this a little bit more, we could write the quantity x plus 3 times, what do we have here? X plus 2 minus root 7. And then x plus 2 plus root 7. And there you go. You've written g of x as a product of linear factors. Make sure you show your work as well. You definitely want to show the synthetic division. If you choose to do long division, that's all right. Notice all this work should be replicated. You definitely want to show all these mathematical procedures. The function below has at least one rational zero. Notice the function below is a polynomial in descending order. Use this fact to find all zeros of the function. If we write this very, very carefully, we know that 7 is actually equal to a sub 3, and then negative 4 is equal to a sub 9. And remember all the possible rational zeros, we'll have the form factors of negative 4, which would be plus or minus 1, plus or minus 2, over plus, and plus or minus 4 over the factors of 7. And what are the factors of 7? 7 is a prime number, so we only have plus or minus 1 and then plus or minus 7. So these are the possible rational zeros. I'm going to bubble this because this isn't actually correct mathematical notation. However, notice we could try to figure out which one is a zero here. Well, let's make an educated guess. Let's try h of 2. So let's evaluate h of 2. 2 is a rational number. And let's see what we get. 7 times 2 cubed plus 9, 2 squared minus 12 times 2, subtract 4. 2 cubed, 2 squared, 12 times 2. Okay, let's simplify this. That's 56 plus, let's say, 36 minus 24 minus 4. I don't think that's 0. That's not 0. So let's try something else. Let's try h of negative 2. Why don't we try h of negative 2? Maybe this will get us somewhere. H of negative 2. I actually, I'm going to move this work. I should have done this work off to the side. I apologize. I'm going to move this really quick. I'm going to move it over here so I could save myself some room. So a lot of times I would do this. I would put my important work aside. What's h of -2? Let's find out. 7 times parentheses raised to the third power plus 9 times parentheses raised to the second power minus 12 times parentheses minus 4. And what goes in those parentheses? A -2. Let's see what we get here. Now we have -56 plus a 36. So that's -20 plus a 24. That's +4, subtract 4. That is 0. Aha! Now by the factor theorem, we know something. By the factor theorem, we know that x minus a -2, which equals x plus 2, is a factor of h of x. All right, we're in business. That allows me to use synthetic division, because notice x plus 2 is monic binomial. A monic binomial is a shortcut. Well, a monic binomial provides a shortcut called synthetic division to do the long division for h of x. We're going to go ahead and divide by x plus 2 using synthetic division. So our 0 is -2. And now we'll write the coefficients, 7, 9, -12, -4. We'll first bring down the 7, and we are going to multiply and add. So this is 7 times -2 is -14. Add it to 9, we get -5. -5 times -2 is +10. Add it to -12, we get -2. And -2 times -2 is +4. Add it to -4, we get 0. Now, this tells us a lot about h of x. H of x is now equal to the quantity x plus 2 multiply to what? 7x squared minus 5x minus 2. And can we factor this? Let's find out. H of x is equal to x plus 2. Well, 7 is nice. We just have 7 times x, and then we have, let's put a 2 here and a 1 here. Well, I think this is going to do it. Oh yeah, it is. There it is. We have written h of x as a product of 3 linear factors. Let's find the zeros. If we find the zeros, we need the output, or the y value, to be equal to 0. And not a total surprise here. You could write really fast. X plus 2 is equal to 0. 7x plus 2 is equal to 0. X minus 1 is equal to 0. So what are our zeros? The zeros for h of x are -2/7, -2, and +1. That's the final answer. Make sure you show lots of work. You gotta show at least the synthetic division. So show work here. Show evidence that you understand mathematical procedures. You also don't forget to write the 0 here. You need this 0 to connect to these zeros over here. Okay. I mean, what does it mean to find a 0 of a polynomial? Well, you have to have the output to be 0, and then we solve for basically the x-intercepts. The function below has at least one rational 0. The function below is a polynomial of degree 3 in descending order. Use this fact to find all zeros of the function. Write exact values. In order to find a zero of the polynomial, we first realize that the output must be 0. So the output is 0, and we are trying to find the x-intercepts, or the zeros of this polynomial. We know it has at least one rational zero, so let's use the rational zeros theorem to find the possibilities. The possibilities of rational zeros. According to the rational roots theorem, we are going to look at this 5 here. And then we want to see the factors of 3 and the factors of 5. The rational zeros theorem says they would have to be having the form plus or minus 1 plus or minus 5 over, let's say, the factors of 3. Factors of 3 would be plus or minus 1, comma, plus or minus 3. So if there is a rational zero, it will take one of those forms. Let's see if we could guess correctly one of the rational zeros. Why don't we try... 1 doesn't seem to work. 1 seems to be too small. Yeah, so 1 doesn't seem to work. How about maybe -1 doesn't seem to work either. We might have to try 5. 5 or -5. Why don't we try f of 5? Let's evaluate f of 5. So 3 times 5 to the third plus 5 squared minus 17 times 5. I don't think this is going to work. I think -5 is going to work. This seems way too big. This is 125 times 3. This is 375 already. Plus another 125. And that's not going to work, right? That's not going to be 0. So why don't we try f of -5? Let's try 3 times the quantity -5 raised to the third power plus 5 -5 squared minus 17 times 5 plus 5. So this is equal to negative, what do we have here? Negative 375 plus 125 minus 85 plus 5. That is not going to work either. Maybe it is -1. Let's try -1. 3 times -1 raised to the third plus 5 times -1 squared minus 17 times -1 plus 5. -3 plus 5. Plus 17. So that's 19 plus 5. This is going to be 24. I mean, not 0. How about that? Well, why don't we try f of 1 doesn't work, so we're left with 1/3. Why don't we try f of 1/3? F of 1/3. F of 1/3 is 3 1/3 raised to the third power plus 5 1/3 squared minus 17 1/3 plus 5. Looks like we're going to need a common denominator of 9. So I am going to multiply things by 3 over 3 here, and then 9 over 9 here. Let's see what we get. This is equal to 3 over 27, so that is 1/9, plus 5/9. What do we have here? Minus 17 times 3 over 9. And then finally plus 45 over 9. 17 times 3 is negative 51. This is going to work. So we have 6/9 plus 45/9 is 51/9 minus 51/9. That is equal to 0. Haha. Finally, we got it. Persistence pays off. What does that mean? That means we have a factor. 0 here is now equal to, what's our factor? Our factor here is x minus 1/3. Oh, but we don't know what's left. So I probably should have done synthetic division right off the bat. I'm going to clear the board here. Let's do synthetic division. And now I really wish I did synthetic division from the beginning. It would have been much faster. So we're going to take our 0, 1/3, and now we're going to write our coefficients of our polynomial. And remember to bring down the 3. Oops, bring down the 3. And we're going to multiply and add. Well, that's really convenient. We're going to add a 1 here. We're going to add a 2 here. And so we get negative 15. And then now we will add a negative 5. And not a total surprise, we get a remainder of 0. That's gorgeous. We need 3x squared plus a 6x minus 15. I'm going to attempt to factor this. Factors of 3 and 15. And I have to somehow get 6. I don't think I can get it. Even though I have 3, 5, 9, 5. I can get 14. I can get 5. I don't think I can get 6. So I'm going to use the quadratic formula. Where are we right now? We're at x minus 1/3 is equal to 0. Or we have what? 3x squared plus 6x minus 15 is equal to 0. And let's put the quadratic formula off to the side here. X is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. And you can see the little a here, you can see b here, and you can see c. What is this expression? This expression is the opposite of 6 plus or minus the square root of 6 squared minus 4 times 3 times negative 15 all over 2 times 3. Let's simplify this. Negative 6 plus or minus the square root of, oh, I forgot a parenthesis here. There we go. That is 45 times 4. So that's 180. 180 plus 36. What's 180 plus 36? That is 216. Probably should have factored out a 4. think this would be a little bit easier. And that is a 54. 54 times 4. Yeah. I'm going to factor out another 9. We get 1 plus 5. So 36 times 6. Oh, of course. Okay. That is 36 times 6. 216 is 36 times 6. Let's factor out a 6 from the numerator. And what do we have left? Plus or minus, whoops, 1. Stop it. Factor out a 6 from the numerator. We have a negative 1 plus or minus the square root of 6 all over 6. So that reduces. There we go. We have it. X is equal to negative 1 plus root 6, or x is equal to negative 1 minus root 6. How many zeros do we have? We have 3 of them. There are your 3 zeros of the polynomial. Make sure you show your work. Show lots of work. Show your synthetic division. Show your quadratic formula. Show your zeros here. And of course, circle your final answer. Let's multiply these two expressions together. There's definitely some significant patterns here. And you got to remember that I squared gets you negative 1. First thing you're going to do is actually reassociate. That is, we're going to associate the x minus 4 and then write a plus 5i for the first term. And then for the second term, we're going to reassociate the x minus 4 and we're going to write minus 5i. I skipped a short little step there. I'm hoping you guys could follow that. Off to the side here, what did I do? I just did x minus 4 plus 5i and then x minus 4 minus 5i. But then I reassociated them. So I went this way and then that way. Now I want to look at this as a difference of two squares. This looks like the quantity a plus b times the quantity a minus b. You know, where a is equal to what? A is equal to x minus 4 and b is equal to 5i. And of course, what do we know about the difference of two squares? A plus b times a minus b yields a squared minus b squared. And we could do this rather quickly. So this is x minus 4 quantity squared minus 5i squared. This is x squared minus 8x plus 16. And then that is plus 25. And remember, I squared is equal to negative 1. I don't know if you've seen this, but it kind of cycles. I cubed, and then what? I to the 4th, and then, well, I take that back. I'm counting wrong here. I meant to say I goes to what? After I times I, you get I squared. And then I squared times I, you get I cubed. And then I to the 4th gets you positive 1. So not a total surprise. And this is equal to what? Down here, this is equal to negative I. Anyways, I should finish the problem. It says to simplify this as much as we can. So the final expression is this. Find a polynomial f of x of degree 4 with real coefficients and the following zeros. You have one zero called negative 1 and has multiplicity of 2. You have another zero called negative 2 plus 3i. The last zero here is a complex zero, and we know that complex zeros of a polynomial come in conjugate pairs, so we certainly know the other zero as well. It's negative 2 minus 3i. That is the conjugate pair of negative 2 plus 3i. We need to find f of x. Well, we actually have all four zeros. The only thing left to do is to multiply everything. So f of x is going to be our expression, and it's going to equal x plus 1, multiplicity of 2, and we're going to have bracket x minus a negative 2 plus 3i, bracket, a new bracket, x minus a negative 2 minus 3i. And let's keep simplifying this. We're going to have x plus 2, quantity squared, is now equal to bracket, not equal, I'm sorry, multiply. Multiply to the quantity x plus 2 minus 3i. And then we also have x plus 2. Now we have plus 3i. So now we have a difference of two squares. We're going to have x plus 1 quantity squared. And now we have a difference of two squares. Not a big deal. This is simply x plus 2 quantity squared minus a 3i quantity squared. And you got to remember that I squared is negative 1. Now we're going to do a lot of multiplying. This is equal to x squared plus 2x plus 1 in parentheses. This is going to be what? This is going to be x squared plus 4x plus 4 plus another 9. We have x squared plus 2x plus 1 times the quantity x squared plus 4x plus 13. And we could multiply this as well. Let's do this off to the side. This is going to equal x to the 4th plus 4x cubed plus 13x squared plus 2x cubed plus a 8x squared plus a 26x plus an x squared plus a 4x, and then plus a 13. Notice with all these positive symbols, it does make the problem a lot easier. So over here, I'm going to write the final answer. X to the 4th plus a 6x cubed plus 22x squared plus a 30 times x, and then plus a 13. Therefore, f of x is equal to x to the fourth plus 6x to the third plus 22x squared plus 30 times x plus 13. Make sure you show your work. Even though I'm going to circle the final answer, make sure you can provide the work. So, circling the assigned work as well.